Hi, in this video we're going to be doing our Unit 12 problem set and the study guide for our acid-base equilibrium unit. So our first question, what is the ionization constant for Ka monoprotic acid if a 0.3 molar solution has a pH of 4.0? So all we know is that this is a monoprotic acid, so we can write Ha plus H2O. Equilibrium is it'll donate proton to water, so it's going to be H3O plus A minus. Now we can do a rice chart or ice chart. 0.3 minus x, 0.3 minus x. This is going to be initial 0, 0, x, x, plus x, plus x. At equilibrium, it's going to be x as well. So now we know pH of 4.0. If it has a pH of 4.0, we can do x is equal to 10 to the negative pH, which is 10 to the negative 4.0, which is equal to 1.0 times 10 to the negative fourth. Now that we know x is equal to 1.0 times 10 to the negative fourth, we can do Ka, we're looking for Ka. Ka is equal to x squared divided by 0.3 minus x. We already know x is going to be this number. And if we plug into our calculator, 1.0 e to the negative fourth squared divided by 0.3 minus 1.0 e to the negative fourth, that will give us an answer of 3.33 times 10 to the negative eighth, which is our answer choice A. Okay, now for number 2, it's asking for us to find the pH of this acid. And we know the acid basically gave us Ka value. Now for the Ka value, we can do ice chart C6H5OH plus H2O is going to donate a proton to C6H5O minus plus H3O plus. It's going to be 0.01 minus x. It's going to be x over here. Now K will be x squared divided by 0.01 minus x. And we know the Ka, which is equal to 1.0 times 10 to the negative 10. And we can find the pH as long as we find the concentration of H3O plus. This one, since the Ka value is so small, we can use the 5% rule, and that is to get rid of this minus x. And now in that case, we can just do 1.0 times 10 to the negative 10 times 0.01 and take the square root of that, which will give us 1.0 times 10 to the negative 6. Now if we do x is the concentration of H2O plus, so if we do negative log of x, that will give us the pH. And we can do that by doing negative log 1.0 e to the negative 6 to get a pH value of 6. Now that we know it has a pH value of 6, we can find that our answer is A. Another way that you can solve for this question is that you know that C6H5OH is not one of the strong acids that we learned, so it's a weak acid, and weak acids won't have a pH of 2, so it has to be A. But this is just a way to show you how I got it. Now next, the student prepares equal molar for each of the following. Which one will have the lowest pH? So NaCl will know it has a pH of 7 because it's a strong acid and it's a strong acid and base cancel each other out. Next, let's see what else we have. Now if we take a look at C, KOH will be a strong base which turns to a weak conjugate acid. H3PO4 is not one of the strong acids that we learned, so it's a weak acid that will turn into a strong conjugate base. So this one will have a pH higher than 7. Na2, same thing, NaOH was a strong base that turns to a weak conjugate acid. H2CO3 is a strong base. No, H2CO3 is a weak acid that turns into a strong conjugate base, and the bases have a pH of greater than 7. Now if we take a look at this, NH4OH is a weak base which turns into a strong conjugate acid. HCl is a strong acid which will turn into a weak conjugate base. Now this is a strong acid, so the pH will be less than 7. And this is the only one with a pH less than 7, so we can know it's the smallest pH. Now next we need to determine the OH concentration in 1.0 molar of C6H5NH2, and he told us the Kb. That's great. So we have C6H5 and H2 plus H2O creates equilibrium with C6H5 and H3 plus OH minus. Now I told us the Kb already, so this is going to be 1.0 minus x, this is going to be x and x. So Kb 4.0 times 10 to the negative 10th, this Kb actually produce OH. Okay, now we can plug this into our calculator. X squared divided by 1.0 minus x, subtract 4.0 e to the negative 10th. With this, we can use a 5% rule actually as well. So let's do that in fact. So we're going to do 4.0 e to the negative 10th times 1 and take the square root of that, which is going to be 2 times 10 to the negative 5th. 2 times 10 to the negative 5th is A. And this is our x value, and our x value is the concentration of OH at equilibrium. Now number 5, just like number 4, except this time we can find the H plus concentration. So we can do nitrous acid, which is HNO2 plus H2O, forms equilibrium with this donates a proton. So NO2 minus plus H3O plus. Now H3O plus is the H plus concentration. They're practically the same thing. Now we have 0.02 minus x, and x. So we can do, and if you're wondering why this is shortened to just this, it's supposed to be a whole right star, but I didn't have enough room, so I just wrote the concentrations at equilibrium. Now we can do 4.5 times 10 to the negative 4, since we told us the Ka is equal to x squared divided by 0.02 minus x. Now we can plug this into a calculator. X squared divided by 0.02 minus x minus 4.5 e to the negative 4th, which will give us an x value of 0.00278. Now that is 2.78 times 10 to the negative 3rd. 2.78 times 10 to the negative 3rd will round to B, 3.0 times 10 to the negative 3rd. Now next, they told us the Ka value, and they asked for the Kb value of SO4. And this is a conjugate acid of SO4. Now since this is a conjugate acid of SO4 2-, we can know that Kw divided by Ka will be equal to the Kb, right? The Kb of the substance is equal to Kw divided by the Ka of its conjugate acid. So now that we know that, we can simply do 1.0 times 10 to the negative 14th divided by 1.0 times 10 to the negative 2nd. And that will give us 1.0 times 10 to the negative 12th, which is A. Next, they ask for the H3O concentration of H3O plus, so we can do, let's first break this all down into Ba2 plus and OH minus, 2OH minus. Now this is 0.05 minus x. Minus x is going to be x, it's going to be 2x, because of the 2 over here. Now since this salt will completely break down into this and this, we know that our x will be equal to 0.05 to fully use it up. And if x is equal to 0.05, that means we'll have 2 times that of OH minus, which is going to be 0.1. Our concentration of OH minus. So concentration of OH minus is 0.1. We can do POH is equal to the negative log concentration of 0.1. So negative log 0.1 gives us 1. Now if POH is 1, pH will be equal to 13. And 10 to the negative 13th power will be the concentration of H3O plus. 10 to the negative 13th power, which is 1.0 times 10 to the negative 13. 1.0 times 10 to the negative 13. It's going to be C. Hey, which one of the following has the lowest concentration of H3O plus? Lowest concentration of H3O plus basically means which one have the lowest Ka. Alright, the lower the Ka, the weaker the acid, the lower the concentration of H3O plus. Now all of these are strong acids, so we can easily get rid of them. Now we just need to debate which one has a weaker Ka value between these two. The one with the lower Ka will have lower concentrations of H3O+. So first we can look at HC2H3O2, HC2H3O2, HC2H3O2 will have 1.8 times 10 to the negative fifth. 1.8 times 10 to the negative fifth. Now NH4Cl will be 5.6 times 10 to the negative 10th power. This one's to the negative 5th power, this one's to the negative 10th power. This one is much smaller, so our answer is E. Now our next, our weak acid HA is ionized by 1%. So this time we really need to do the right turn. So HA plus H2O is going to form H3O plus A minus. Now we have 0.01 to start off with, and we're going to subtract it by x. What is x? Only 1% is ionized. So what is 0.01 times 1%, which is 0.01? It's going to be 1.0 times 10 to the negative fourth. This one will be 0 plus 1 over 1, 1.0 times 10 to the negative fourth, plus 1 over 1, 1.0 times 10 to the negative fourth. So what is 0.01 minus? Actually, that's enough for now. This is going to go down here, this is going to bring down here, and this is going to go down here as our equilibrium values. Now we have Ka. It's looking for the Ka. Ka is equal to 1.0 times 10 to the negative fourth power squared divided by 0.01 minus 1.0 times 10 to the negative fourth. And you can easily do that in calculator. 1.0 e to the negative fourth squared divided by 0.01 minus 1.0 e to the negative fourth will give us an answer of 1.01 times 10 to the negative 6. 1.01 times 10 to the negative 6. 1.01, which runs to 1.0 times 10 to the negative 6, which is A. Now number 10, what is the volume to get 20 milliliters of that? Okay, so to be diluted when the solution has a pH of 1.3. Now the pH has 1.3, 10 to the negative pH's power is going to be the concentration of H3O plus. Now 10 to the negative 1.3 is going to give us the concentration of 0.0501. Now we have that. We can do M1V1 is equal to M2V2 because we're dealing with dilution. Now M1 is going to be 1 molar times 0.02 V. Actually, no, we don't have to do liters. We can do milliliters. ml is equal to L, we keep the other side milliliters as well. We're looking for the molar. We're looking for the volume. So we just found the molar of the new solution. So it's going to be equal to 0.0501 molar times x ml. So we do 1 times 20 divided by 0.0501 to give us an answer of 399.2. What is this? Milliliters. Now, if this is milliliters, it rounds up to 0.4 liters, which is our answer choice C. Number 11, the pH of a 0.01 molar solution. So Na2CO3, Na2CO3. 2 minus Na is a group 1, so it has no affinity for water, so we're only dealing with CO2 3 minus, CO3 2 minus, sorry, plus H2O, which this will donate an acid. This is H2O is the acid over here, which donate a proton into HCO3 minus plus OH minus. Now looking for the pH, so we need to know the concentration, so we need to know X value. So we have 0.1 minus X, this is going to be X. So what is the K of HCO3? K of H2CO3 is going to be K2. We're dealing with K2 because of the CO3 2 minus and HCO3 minus. So K2 is going to be 4.8 times 10 to the negative 11. So 4.8 times 10 to the negative 11 Now that we have our K value, we can do KW divided by K to get our KB for our base, because we're dealing with a basic solution. Now this is going to be equal to, let's see, 1.0 e to negative 14th divided by 4.8 e to negative 11th to give us 2.08 times 10 to the negative 4th. Now if we plug that into the x squared divided by 0.1 minus x, to find our x value, we can get x as equal to, now that we have our Ka, we can use Kw divided by Ka to find our Kb, because after all we're dealing with a basic solution. We need our Kb before we can do anything, and it's 1.0 e to the negative 14th divided by 4.8 times 10 to the negative 11th will give you 2.08 times 10 to the negative 4th. Now if you make that equal to the equilibrium, x squared divided by 0.1 minus x, you can plug that into the graph and do second 0, which will give you an answer of x is equal to 0.00446. Now if you do negative log of 0.00446 and 14 subtract that, you'll get an answer of pH as 11.65. pH of 11.65, which is our answer C. For number 12, we need to find the percent ionization, and we can do that by setting up our right chart and see how much is ionized. Plus H2O makes H3O plus F minus. 2.2 moles per liter is 2.222 molar. 0 plus X it's going to be 0. No, this would be minus X. This is 2.22 minus X at equilibrium. It's going to be X at equilibrium, and I told you the K, the equilibrium expression is going to be 7.2 times 10 to the negative 4th is equal to X squared divided by 2.22 minus X. Now we can plug X in to find our final solution of F minus X squared divided by 2.22 minus X minus 7.2 e to the negative 4th. We can get X as 0.0396. Now we need to use this number, our final 0.0396 divided by our initial, which is 2.22 molar, which will be, and don't forget to multiply by 100 to find the percentage. The answer gives us 1.78, and since we're going to multiply by 100, it's going to be 1.78%, and 1.78% matches is approximately 2%. Next, how many moles of pure NaHSO4 will be needed to prepare 1 liter of having pH of 2.0? To start off this, we can find NaHSO4, and we'll know that Na has no affinity for water. So it's going to be HSO4 minus plus H2O forms equilibrium, and since it has pH of 2.0, that means it's acidic, so it'll be donating a proton. It's going to be SO4 2 minus plus H3O plus. Now, how many moles of pure NaHSO4 will be required to prepare 1 liter solution having a pH of 2.0? Okay, so 10 to the negative pH's power is going to be equal to 10 to the negative second power, which would be 1.0 times 10 to the negative 2, which is a concentration of H0 plus, aka our X. So plus X is going to be equal to 1.0 times 10 to the negative second, 1.0 times 10 to the negative second. Over here, this solution will be a different X minus X will be our initial for H2SO4, which is what we're finding, minus our X for the concentration of H3O plus. So this is what our equation will be, and now we need to find the Ka2. So Ka2 for H2SO4 will be 1.2 times 10 to the negative second power. 1.2 times 10 to the negative 2 is equal to 1.0 times 10 to the negative 2 squared divided by x minus 1.2 times 10 to the negative second. No, 1.0 times 10 to the negative second. So on top we have 1.0 e to the negative second squared. On the bottom we have x minus 1.0 e to the negative second. Subtract the 1.2 e to the negative second. And now that will give me an x value of 0.01833. And to remind, this x value, maybe I kind of made it confusing, but this x value is not the concentration of H2O plus at equilibrium. Where we found that was this x value over here. We substitute that in. Now, this x value that we just found is by using the equilibrium formula to find, using the equilibrium equation to find x, this x, which should be the initial of our NaHSO4, and we found that to be 0.0183, which runs to A, 0.018. Okay, next 0.01 mole, 0.01 mole of NaA. What is Kb for A minus? Okay, so this one we're gonna do NaA plus H2O forms equilibrium with, again, Na has no affinity for water, so this will just be A minus, it will receive a proton, it will be Ha plus OH minus. Now we have 0.01 mole. Okay, now we just have to use everything just to make 1.0 liter solution. We're gonna have to use everything as moles. So this will be 0.01 mole. This is gonna be 0, 0. This is gonna be minus x. This is gonna be plus x. Again, we have our pH. So that tells us our POH. It tells us that our concentration of OH minus is equal to 10 to the negative POH's power, which is equal to 10 to the negative 14 minus 11.95. What is that going to be able to be? 10 to the power of negative, parentheses 14 minus 11.95 gives us 0.00891. That is our x value. Now we're looking for the Kb for A minus. So this is already Kb, great. So Kb is equal to x squared divided by 0.01 moles, which minus x, sorry, here minus x, which is equal to x, which we already found, 0.00891 divided by 0.01 minus 0.00891. Now if we were to plug that in your calculator, 0.00891 squared divided by 0.01 minus 0.00891 gives us 0.0728, which is 7.28 times 10 to the negative third power. 7.28 times 10 to the negative third power, which is, sorry, 7.28 times 10 to the negative second power, which is our answer choice for A. And that would be the Kb, since our equation involves a OH minus. Now this may ask, what is the pH of a 0.1 molar hydrogen sulfide? Hydrogen sulfide is H2S plus H2O will form equilibrium with HS minus. Because remember, protons can only be donated one at a time, plus. Now we have 0.1 molar minus x, so plus x plus x. So we'll have Ka is equal to x squared divided by 0.1 molar minus x. Now it told us the K, and how do you know which K to use? Well, this is going to be K1. This is going to be K1, and K2 will be HS minus plus another water to form another H2O plus and S2 minus. So this is the first step in the reaction, so this we'll be using K1, and K1 is equal to 1 times 10 to the negative 7th. And this will give us our pH for the hydrogen sulfide solution. And we can apply the 5% rule over here since the K value is so small. So we're going to get rid of this plus x minus x over here. Now we're going to do 1.0 e to the negative 7th times 0.1 and take the square root of that, which will be 1.0 times 10 to the negative 4th. Now this is the concentration of our H3O plus, and this is x. Now we just need to take the negative log. And since this is acidic solution, we can just take the negative log of 1.0 times 10 to the negative 4th, and it will give us the pH, negative log 1.0 e to the negative 4th, which is 4. So our final answer is a pH of 4. So first acid is H2SO3 plus, let's put that into water, which forms equilibrium with HSO3 minus plus H3O plus. However, that is not enough because we need this concentration of SO3 2 minus. So we're going to do a second step, donating our second proton as well, plus H2O forms equilibrium with SO3 2 minus, which is what we need over here, plus H3O plus. Okay, so now first we're going to use 0.1 molar minus x and the x over here. So this is our Ka1, this is our Ka2. So first, our Ka1 is 1.5 times 10 to the negative second. 1.5 times 10 to the negative second power is equal to x squared divided by 0.1 minus x. So let's quickly plug that into calculator as well. X squared divided by 0.1 minus x minus 1.5 e to the negative second power. Okay, that will give us an x value of 0.0319. Now this x value is going to be here and here. So SO3 plus this SO3 plus, instead of starting off with 0, we're going to be starting off with x value, which is 0.0319. So instead of starting with 0, we're going to have started with 0.0319 because we already produced some H3O plus over here. And now S3O minus as well is going to be x value, which is 0.0319. Now SO3 2 minus, we didn't produce any in the previous one, so this one's going to remain at 0. This is going to be minus x, and this one is going to be 0.0319 minus x. This is going to be plus x. This is going to be x over here. This is going to be plus x. This will be x over here. So our final formula for Ka2 is equal to x times 0.0319 plus for equilibrium over here, plus x divided by 0.0319 minus x, which is this, our product divided by our reactant. Now we need to go to our y equals formula. And do x times 0.0319 plus x divided by 0.0319 minus x, subtracted by K2, which is 1.0 times 10 to the negative 7th. And this will give us an final x value. And again, x is our SO3 2 minus, so let's see what this final x value will be. Our final x value will be 9.9999 times 10 to the negative 8th, which rounds up to 1.00 times 10 to the negative 7th. Alright, 9.999 times 10 to the negative 8th rounds up to 1.0 times 10 to the negative 7th, and that is our answer for C. So our final answer for this one is going to be C. Now, next question, it asks us to identify the conjugate base in pairs. So, okay, so this is easy. We just have to label which one's the acid, which one's the base. Br minus is receiving the proton in our reactants. So this is going to be the base. Bases receive protons. And if this receives a proton, that means this gives a proton, which means CH3OH is the acid. Now the one who receives is going to be the conjugate acid in the product, and the one who donates will be the conjugate base. And that's it. Our our CH3OH will donate a proton to Br. Okay, that's it for number 17. Number 18, identify the stronger acid in each pair and justify our choice. Now this one, our answer, which one's stronger, is going to be Br, HBr, because it has a larger atomic radius. With a larger atom, it also has a longer bond length between the H and the Br. The longer the bond means the weaker the bond, which allows the H plus to leave easier, which allows the H in the HBr to leave easier, to get dissociated in water faster, and this means a stronger acid. Now, second one, H2SO3 or H2SO4. Now, this is easy. Maybe H2SO4 because it has more oxygens. Adding oxygen to the central atom causes a shift in electric density towards the central atom. And we call that the inductive effect. Now, this causes the H2SO4 to be more polar, and more polar means it's easier for the water to attract the H plus, aka allowing the H plus to leave easier in the previous question, which means the acid is stronger. Okay, so now this one we have an acid and we're gonna place it in water. So HC3H5O2 plus H2O, since it's a weak acid, we're gonna use a double arrow, and it's gonna be donating a proton. So it's gonna be C3H5O2 minus plus H3O plus. Now this is aqueous. This is aqueous. Water is liquid. This is also aqueous. Now this is balanced, and write the K expression. Ka is equal to the concentration of H3O plus times the concentration of C3H5O2 minus divided by the concentration of HC3H5O2. And you will not include H2O because it's liquid. Now calculate Ka if we have 500 milliliter solution and 9.250 grams. Okay, so let's first use what we have, 9.250 grams, and 1 mole has how many grams? Let's see, we're doing with HC3H5O2, so it's going to be 1.01 plus C3, 12.01 times 3 plus 1.01 times 5 plus 16 times 2, which should give us 74.09. 74.09. Now 9.25 divided by that should give us 0.1248 moles. Now we divide it by our liter to find molarity, which is 0.5 liters. Divide that by 0.5 liters, and we should get an answer approximately 0.2497 molar. Okay, now with that we can use our HC. We can write our rice chart plus H2O forms equilibrium with C3H5O2 minus plus H3O plus. Down here it will be, we start off with 0.24797 minus x, 0.2497 minus x. I'll just write the rest real quick. It's going to be 0, 0, plus x, it'll be x, and x. Alright, now we need to calculate K, right? So K can be calculated using our pH. So we have pH equals, we have concentration of H3O plus is equal to the 10 to the negative pH's power, which is 2.73, 10 to the negative 2.73 power is equal to 0.00186. So instead of all the x's, we're going to replace them with 0.00186 plus 0.00186 plus 0.00186, which gives us 0.186, 0.00186. 0.2497 minus 0.00186 gives us 0.2478. Now K is this. So it's going to be 0.00186 squared divided by 0.2478, which will be 0.00186 squared divided by 0.2478 gives an answer of 1.39. So our answer K is 1.396, which runs to 1.40, and we will run to two significant figures because that's how much pH we're given, times 10 to the negative fifth. So that is our K value. Now a different solution is prepared. Okay, so this time we have 1.5 grams, and it's still going to be the same. So in the previous problem we found it as 74.09. Actually, I'll write it to a 7 more. Yeah, this time we're just given with 1.5 grams, 74.09. Is that right? Yeah. Grams, 1 mole of C3H5O2, C3H5O2. So 1.5 divided by 74.09 gives us 0.0202 moles. And now we have a 2-liter solution, which means divided by 2, we're going to get 0.0101 molarity. Now we can use our rice chart again. HC3H5O2 plus H2O forms equilibrium with C3H5O2 minus plus H3O plus. This time we're going to use 0.0101 molar. This is a 1, sorry. And this is going to be 0, 0, minus x, plus x, plus x, 0.0101 minus x. So it's going to be x and x over here. Okay, now what is the pH? So in order to find pH, we need to use our concentrated of H3O plus, and we can do so by using Ka. And we found the K in the previous problem, so we can use 1.4 times 10 to the negative fifth power is equal to x squared divided by 0.0101 minus x. So we're going to use, go to our y equals, we're going to use x squared. Down there, we're going to use 0.0101 minus x. Subtract 1.4. E to the negative fifth. Graph it, and this should give us our x value. It will give us 3.69 times 10 to the negative fourth power. Now we're going to use negative log of 3.69 times 10 to the negative fourth to find pH, which will be negative log of 3.69 e to the negative fourth, which will give us a pH of 3.43. For E, we're asking if this is acidic, basic, or neutral. Alright, this is going to be easy. NaCH3H5O2. Na does not have affinity for water, but let me just show you. NaOH is a strong base because it's group 1, which will make our Na minus a weak conjugate acid. Now this, when in water, is going to attach to a H, and this is going to be a weak acid, which will turn into a strong conjugate base, which means this is a strong conjugate base. And now we have a weak, which means it's neutral, and we have a strong base, which means it's going to be basic. We have a basic and a neutral, which means the overall will be basic. And how do we prove that? Well, Na has no affinity for water, so by the equation, 5O2 plus H2O, aqueous liquid, forms equilibrium with, let's see, donates this is going to be minus. So it's going to attract an H. It's going to be H, C3H5O2 plus OH minus. Aqueous. Since we have an OH minus, that means it's basic. Calculate the KB. Okay, so first let's use the Ka of its conjugate acid, which is this. HC3H5O2. Let's see, HC3H5O2. HC3H5O2, 1.3 times 10 to the negative 5th power. 1.3 times 10 to the negative 5th power. So C3H5O2 minus will be, the Kb for this will be the Kw divided by the Ka of its conjugate acid, which is going to be 1.0 times 10 to the negative 14th divided by 1.3 times 10 to the negative 5th. 1.0 e to the negative 14th divided by 1.3 e to the negative 5th will give us an answer of 7.69 times 10 to the negative 10th power, and that is our Kb. So for this problem, we're going to have to find every single species, and we can do so by writing our hydrolysis first. Again, Na is a strong base which turns into a weak conjugate acid. Na is a weak conjugate acid which will not undergo hydrolysis, so this is the only thing that's going to undergo hydrolysis. We can add water to it, plus H2O, forms equilibrium as H, C3H5O2 plus OH minus. Because this is a base, it's going to accept a proton. And now we're going to have to use we're going to have to find molar without giving information. We have 20 grams and 1 mole of C3H5O2, NaC3H5O2. Na is 22.99 plus 12.01 times 3 plus 1.01 times 5 plus 16 times 2 gives us 96.07. 20 divided by 96.07 gives us 0.20818 moles. Divide that by 0.750 liters will give us approximately 0.278 molar. Now this is going to be 0.278 molar ice. It's going to be minus x, 0.278 minus x. It's going to be 0, 0 plus x, x. Now we're going to use because we're producing OH, we're going to have to use Kb value, and Kb value we found over here, so I'm going to bring this down. 7.69 times 10 to the negative 10. 7.69 times 10 to the negative 10th is equal to x squared divided by 0.278 minus x. Now we're going to use our y equals 0.27 x squared divided by 0.278 minus x subtracted by 7.69 times 10 to the negative 10th. Graph it, and this will give us our x value of 1.46 times 10 to the negative 5th power. Now that will be our x for this, and we'll be subtracting this over here as well. So what is the molar for Na? Well, Na does not undergo hydrolysis, and it basically acts as a spectator ion. So then however much we start with is however much we end with. We start with 0.278, so we end with 0.278. Molar of C3H5O2 minus, well, it started with 0.278 and ended with 0.278 minus x. So if we do 0.278 minus 1.46 e to the negative 5th, it's going to give 0.2779, which is 0.278. Now for this, it's going to be our x value, which is 1.46 times 10 to the negative 5th power. OH, same thing, 1.46 times 10 to the negative 5th molar. Now this H3O plus, we're going to have to, it's going to be a little bit tricky. First, let's find POH. Alright, POH is equal to the negative log concentration of OH minus, which is x, which is this. Alright, negative log of 1.46 e to the negative 5th is 4.8356. Now if we do 14 minus that, it will be 14 minus, let's run to 3 sig figs. Yeah, let's run to 3 sig figs. 9.164. Now 9.164 is pH. 9.164, and the molar of H3O plus is going to be concentration of H3O plus is going to be the 10 to the negative pH's power, which is 9.164. 10 to the negative 9.164 gives us a concentration of 6.85. So our concentration of H3O plus is going to be 6.85 times 10 to the negative 10th power times 10 to the negative 10th power. And that is how we do G. Now we need to rank the following acids with strongest to weakest. Alright, so let's see what we can find here. NH4 plus is a base. So this is obviously going to have the, oh, perfect, the Ka, I didn't even realize that. So just organize them by the strongest to weakest Ka, right? The lower the Ka, the weaker the acid. So our lowest is going to be H4 plus. Then, let's see, times 10 to the negative 6 is going to be stronger than this. Our C5H5NH plus is going to be stronger. I'm going to cross this out. Then we're going to have to compare against these two. One's 1.8 and one is 7.2. 1.8 is less than 7.2. So it's going to be HCOOH and then 7.2 times 10. Oh, sorry. And finally we have HNO2. Alright. Ordering from greatest to least, and it can be easily determined by looking at the Ka. Now predict whether each solution is acidic, basic, or neutral, and write equations for any hydrolysis that occurs. So NH4 OH will be a weak base, which turns into a strong conjugate acid. HI is a strong acid, which will turn into a weak conjugate base. Now this is going to be neutral, and this strong acid is going to be acidic. So this overall is going to be acidic. And to prove our equation, we're going to use NH4 plus H2O. Again, the I minus will not be included because it is a weak conjugate base. And it will just be sitting outside during, it will not undergo hydrolysis and just sit outside being an expected ion. Makes, because it's a cation, it's going to take OH with it. It's going to be NH4 OH plus H plus. Because of the H plus over here, this is going to be acidic. Now, KOH is a strong base, which turns into a weak, which makes K plus a weak conjugate base. HNO3 is also a strong acid, which makes NO3 minus a weak conjugate acid. No, sorry, this is the weak conjugate acid, and this is the weak conjugate base. Since both of these are weak, both of these are neutral, and when both of these are neutral, both of them will be neutral. And when it's neutral, there will not be any hydrolysis reactions because they don't undergo hydrolysis. Next, we have NaOH, which is a strong base, which makes Na a weak conjugate acid. HClO, which is a weak acid, which makes ClO a strong conjugate base. Now, with a strong conjugate base and a neutral, and basic, overall is going to be basic. And we can use ClO minus. Na will not be included because it's from group 1. Group 1 will not undergo hydrolysis. Plus H2O makes equilibrium with it's the anion, so it's going to take an H with it. CO plus OH minus. From the OH minus, it can prove our basic solution. Okay, so we're given with this equation, and we're asked to write the equilibrium constant expression. Because we're dealing with OH, it's going to be Kb. Our equilibrium constant is going to be Kb, and it's going to be concentration of OH minus times the concentration of NH4 plus divided by, we do not include H2O because it's a liquid, H3 and H3. And that is it for part A. Part B, we determine the pH of 0.10 molar. So we're going to write our equation again. H2O liquid, equilibrium with NH4 plus aqueous plus OH minus aqueous. Oh, and up there, I think it's best if I include all the states of matter: aqueous, liquid, aqueous, 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 liquid, aqueous. So here we are over here, and we have 0.0180 molar minus X equals 0.180 ICE. It's going to be, we're going to cross this out, 0, 0, plus x, x. We need to find the KB, right? Ka of NH4 plus, Ka of its weak conjugate acid. So Ka of the weak conjugate acid is going to be Ka of NH4 plus. Sorry, not weak. Ka of its conjugate acid is going to be NH4 plus. Let's look for NH4 plus. 5.6 times 10 to the negative 10. Over here. Sorry. Over here. 5.6 times 10 to the negative 10. So if this is 5.6 times 10 to the negative 10th, then Kw divided by Ka will get us our Kb for our NH3, which will be 1.0 divided by 5.6. Can't remember. Ready? 5.6 e to the negative 10th power. On top is going to be 1.0 e to the negative 14th. It's going to give you Kb as 1.786 times 10 to the negative 5th power. Now if you set that to x squared divided by 0.018 minus x, sorry, I forgot about over here, go to y equals 0.018 minus x minus 1.786 e to the negative 5th. It would give us an x value of 5.58 times 10 to the negative 4th. Now, 5.58, we can find the pH by using 14 plus log of this, which will be equal to 14 plus log of 5.58 e to the negative 4th. It's going to give us a pH of 10.747. 10.747. Now, determine the value of the base ionization constant Kb. Well, we just did that, right? It's over here. We found the Kb on the previous problem. It's 1.7 times. It's 1.78 times 10 to the negative 5th. So we can just pull that over here. We can rewrite it. Kb is equal to 1.786 times 10 to the negative 5th power. Now, determine percent ionization. Alright, so in the end, we ended with x value, which is our overall, in the end, our NH4 plus is going to be x value, which is 5.58 times 10 to the negative 4th. When divide that by our original, which is 0.0180. So 5.58 e to the negative 4th divided by 0.0180. Don't forget to multiply by 100 to find the percentage. Times 100 will give us 3.1%. Now, number 23, consider the titration of this. You may assume the 5% rule holds, and without checking, we gotta find the pH. Alright, calculate the initial pH of the solution. Alright, HF aqueous plus H2O liquid, H3O plus F minus, right? We're putting this in water first. So this is going to be 0.1 molar minus x. This is 0.1 minus x. It's going to be 0, 0 plus x, x. So our Ka is going to be x squared divided by 0.1. And we do not include the minus x because it told us to assume the 5% rule holds. Now we define K. So now we define x. We're looking. Now from here we can tell that HF is 7.2 times 10 to the negative 4th. So this is going to be 7.2 times 10 to the negative 4th power. Now with that we can easily find x. So it's going to be 7.2 e to the negative 4th times 0.1 and take the square root of that. Right? Multiply both sides by 0.1 and take the square root. And the 5% rule is when you basically take out this x minus x over there, and when you do that, you don't have to graph it anymore. You just multiply both sides by 0.1 to cancel out this, and then take the square root to take out this, leaving you with x, and our x is 0.00849. Now, with x, our x is a concentration of H2O plus, so negative log of x will give us a pH. Negative log of that will give us a pH of 2.071. That is our pH of 2.071. So now we need to calculate the pH of after adding 10.0 milliliters of NaOH. And to do that, we're going to create a Rebecca chart, RBCA, of HF plus NaOH, making, let's see, Na has no affinity for water, right? And it's a group 1 alkali metal, so it will not be included, and we're going to cross Na out, which forms F minus plus H2O. Now, we start off with 100 milliliters and 0.1 molar. So if we do 0.1 molar is equal to X divided by 0.1 liters, it's going to be 0.1 times 0.1, which is equal to 0.0100 molar. So this is going to be 0.0100 over here, and 0.0100 over here. Nope, sorry. For the concentration of NaOH, it is 0.200 molar, 0.2 molar equals X divided by our volume, which is 0.01 liters. Now 0.01 times 0.02 will give you 0.00200. And now that will be the concentration over here, 0.00200. So it'll be 0 for initial, and it's going to be, which one's the limiting reactant? This one's the limiting reactant, so it's going to be minus 1 over 1 times 0.00200. It's going to be minus 1 over 1, 0.00200. It'll be plus 1 over 1, 0.00200, and water, we don't really care about it. So this will be 0.1 minus 0.01 minus 0.002 is going to be 0.00800. This will be 0, and this one will be 0.00200. Now with this, we can apply it to the rice chart. After we find the concentration, we can apply it to the rice chart to find the pH. And the rice chart will include HF plus H2O, like what we did up there, forming equilibrium with H3O plus F minus, since this acid will be donating a proton. And now this is all in molar, but for rice chart, we need to find everything in moles. No, in moles. This is all in moles, and for the rice chart, it would have to be molars. So we can do 0.00800 and 0.00200, right? These two are the moles over here. And now we need to assume that volumes are additive. So in the beginning, we have how much? We have 100 milliliters. Now we add 10 milliliters, this is going to be 0.110 liters. This is also going to be 0.110 liters. Now if we do 0.008 divided by 0.110, that will give us, this is going to be 0.0727 molar, and this is going to be 0.002 divided by 0.110, which will be 0.182 molar. Now we're going to plug that out over here. HF, the original, is going to be our number over here, which is the corresponding molar, 0.0727. H2O, we cross it out, we don't really need it. H3O plus, we start off with 0, and F minus is 0.00200 moles, which is 0.0182 molar. And we need to use everything in molar because it's the rice chart. Now it's going to be minus X, it's going to be equilibrium, 0.0727 minus X, it's going to be X plus X plus X, be 0.0182 plus X. Now we can grab the Ka. Ka of HF is 7.2 times 10 to the negative 4th. So we go back, and K equals 7.2 times 10 to the negative 4th, which is equal to X times 0.0182, and we don't have the plus X because it said assume the 5% rule holds. So we will not include the plus X and divide it by. On the bottom, it's going to be the same thing. It's going to be 0.0727 727. We'll not include the minus x because we need to assume the 7% rule holds. Now this is really simple. We can do 7.2 e to the negative 4 times 0.0727, divide that by 0.0182 to get us a pH, to get us a kx value, not pH, x value of 0.002876. Now if we do negative log, because this is our concentration of H3O+, we do negative log of x, so negative log of that number, and it will give us 2.541. And that is our pH after adding 10 milliliters of NaOH. Now C is the same thing, except this time we're given with more milliliters. So it's going to be 0.2 molar of NaOH from up there in our equation, divided by x, divided by 0.025 milliliters this time. So this time is basically 0.2 times 0.025, which gives us an x value of 0.005 moles. Our HF remains the same. So it'll be HF plus NaOH. Again, the Na doesn't really do anything over here, so I don't need to worry about it. Plus H2O. So this will be, this one stays the same because our original concentration of HF does not change. This is going to be 0.005 this time. So it's going to be 0 and 0. Which is limited reactant? This is the limited reactant. So it's going to be subtract 1 over 1, 0.005. It's going to be subtract 1 over 1 times 0.005. It's going to be plus 0.005. And it's going to be, I'm going to cross it out. It's going to be 0.005 left, 0.005 over here, and 0.005 over here. Now we need to, since everything is 0.5, we need to do 0.05 divided by our volume. And since volume is, we need to assume it's additive, it's going to be 100 milliliters up there, plus the 25 milliliters we just added, which is going to be 0.125 liters. 0.005 divided by 0.125 liters gives you 0.04 molar. Now we can plug that into a rice chart. The equation reaction is going to be HF plus H2O, same as before, forming H3O plus F minus. And we should use this equation because it gives the H3O plus. Now the initial for HF, as we found, is going to be 0.04 molar. Water, we don't care. This is going to be 0 molar because we didn't end up with any H2O plus in the previous one. F minus is the same as previous. So this is also going to be 0.04 molar. Is minus X, then be X. This is going to be 0.04 minus X, then be plus X. This is going to be minus X. 0.04 minus X. Again, since the 5% rule holds, so we're going to cross out all of these, and we're going to use the same K as above because we're still dealing with HF. So this will be, let's see, 0.04 times X divided by 0.04 equals our K, which is 7.2. 7.2 times 10 to the negative 4th. And that means the 0.4 and 0.4 will cancel out, which means 7.2 times 10 to the negative 4th is equal to X. Now if we do the negative log of X, we can get pH of negative log 7.2 e to the negative 4th, which is 3.143. And again, it's 0.4 divided by 0.4, so I can simply plus it out, leaving us only X. Third, calculate the pH after the addition of 40 milligrams. So it's practically the exact same thing as we just did. Maybe 0.2 molar equals X divided by 0. This time is 0.4. So 0.2 times 0.04 will give us 0.008. So we do rice. HF. Oh, sorry. This is RBCA. My bad. RBCA. To be HF plus NaOH makes F minus plus H2O be 0.0100. It's going to be 0.00800. It's going to be 0.0. No, this is 0.0. This is going to be crossed out. This is going to be 0.01. Sorry. This one is limited reactance. It's going to be minus 1 over 1, 0.00800. It's going to be plus minus 1 over 1, 0.00800. It's going to be plus 1 over 1, 0.00800, which means this will be 0.00200. This is going to be 0, and this is going to be 0.00800. So when you grab 0.08 and 0.02 divided by our new volume, which is this time 140 milliliters. So 0.140 liters divided by 0.140 liters, 0.08 divided by 0.140 gives us 0.571 mole, and 0.02 divided by 0.140 is going to give us 0.143 molar. Now we can set up the Rice chart, and it's going to be same thing as for HF plus H2O form equilibrium with H3O plus F minus. HF is new concentration going to be 0.0200. Water, cross it out, this is going to be 0. F minus is going to be 0. Oops, we're supposed to use molar, right? So this is going to be 0.143. This is going to be 0.571. And I forgot a 0, sorry. 140, this is going to be 0.057. Extra 0 over here and extra 0 over here. So it will be extra 0 over here and extra 0 over here. Now this is going to be minus x, this will be 0.0143 minus x, it will be plus x, plus x, 0.0571 plus x. Now our HF is going to, Ka is going to remain the same, so 7.2 times 10 to the negative 4 is equal to x times 0.0571 divided by 0.0143. Now, if we do 7.2 e to the negative 4th times with 0.0143 divided by 0.00571, and now this will give you an x value of 1.803 times 10 to the negative 4th. Now, pH is equal to the negative log of that, which will be equal to 3.744. Now next we need to calculate the pH at equilibrium, at the equivalence point. And remember, the equivalence point is when the moles are equal. Now how much moles do we, okay, so when the moles are equal, HF plus NaOH makes F minus plus H2O. That means both of these will be completely used, right? Because they are equal molar and because they're equal, they have the equal number of moles, which will be completely used, forming HF minus plus H2O. Now this will form another reaction, and that is, because there is no more any of this left, it will form another reaction, and that is HF plus OH minus. Now let me write it on the side. Moles of H plus equals moles of NaOH. Now I have 0.1 molar times 0.1 liters equals equals 0.2 molar, right? The H plus we're given with 0.1 molar in the beginning, and NaOH minus NaOH we're given with 0.2 molar from up there. 0.1 and 0.2. Now down here, times 0.2 times x liters, and if you solve for x, it will be 0.001 divided by 0.2, 0.01 divided by 0.2 gives you 0.05. So x 0.05. So there will be 0.05 liters of NaOH in order for it to be equal molar. Now in this case, 0.1 molar times 0.01 is going to be equal to 0.01 moles, which will be equal to 0.01 moles. Alright, now they're equal molar. Now we can use 0.01 moles. Right, when these two are multiplied, 0.01 moles, both of them are 0.0 moles by the new volume, which is 0.1 plus 0.05 liters. Alright, so 0.1 plus, we're basically adding 50 milliliters of our NaOH. So our original 100 milliliters plus 150 plus another 50 is going to be 150 milliliters. So 150 liters. So 0.01 divided by 0.150 will give us 0.0667. Now we're going to use Ka of HF is equal to 7.2 times 10 to the negative 4th. That means the Kb of F minus is because we're producing OH and we're dealing with F minus, so we must find Kb. So we're going to do Kw 1.0 e to the negative 14th divided by Ka, which is 7.2 e to the negative 4th, to get us the Kb of 1.389 times 10 to the negative 11th. Now with Kb, we can set that equal to, let's see, this is going to come down to x, this is going to come down to x, this is going to come down to 0. Our molar. So basically doing what we did before, x squared divided by 0.0667, which is the molar that we found, and this molar is a molar for HF and NOH that gets completely used to form F minus. So F minus is our molar of 0.667. There will be minus x over here, which makes it equilibrium of 0.667 minus x, but that will not be, the minus x will not be counted due to our 5% rule. So on the bottom is going to be 0.667 HF and OH minus. Since these two since our original products only produced F minus and H2O, so there will be none to start off with, which means there will be plus x and plus x, which means there will be a plus x over here and a plus x over here, which means there will be x and x at equilibrium, which is where I got my equation from, which is where I got this from. Now we can simply solve for x as 1.389 e to the negative 11th times 0.06667, takes the square root of that, and I'm going to get x as 9.625 times 10 to the negative 7th. X is the concentration of OH minus, so pH will be equal to 14 plus log of x, which is equal to 14 plus log of what we have up there. It's going to be 7.983. And that is our pH at equivalence point. Now for F, we need to calculate the pH after the addition of 80 milliliters. And again, it's going to be the exact same of what we did up there. HF plus NaOH makes F minus plus H2O. This time, there will be 0.01 from we started. Now 80 milliliters, 0.2 molar equals X divided by 0.08. So 0.2 times 0.08 is going to give you 0.016. So it'll be 0.016. It'll be 0 and 0. Now be careful this time. Which one is the limiting reactant? The limiting reactant now is the HF. So it's going to be 0.01 minus 0.01 minus. It'll be plus 0.01. This will be crossed out. So this will be gone. This will be 0.006. This will be 0.01. Now, because we don't have any HF left over to do the second part of the right chart, HF plus NO2, we're going to simply use what we have. Right? NaOH will be our concentration. NaOH, that number of moles, will be our concentration. Will be our moles for OH minus, because the Na doesn't really count in this reaction, right? Na is going to be a spectator ion. So it's going to be OH, and this is our concentration of OH minus. This is moles of OH minus. So OH minus is going to be, concentration is going to be moles divided by liters. How much liters do we have? It's going to be 0.180, because we have our original 100 milliliters plus the 80 milliliters. So this moles divided by liters is going to be the concentration of OH minus. 0.06 divided by 0.180. It's going to give us 0.0333. Now that I have a concentration of OH minus, pH will be 14 plus the log of x, or 14 minus the negative log of x minus of x. Now this will be 14 plus log of x, which will give us a pH of 12.523, and that is our pH. Now finally, we need to graph off those, and on the x-axis we're going to be titration curve. Titration curve, the x-axis is going to be milliliters. On the y-axis is going to be pH. So let's start. We're going to need 80, right? This is going to be 80. 2, 4, 6, 8, 10 is going to be 10. It's going to be 20. 25. No, sorry, 30. 30. 40, 50, 60, 70, 80. Alright. pH is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, let's see. When we add, this is milliliters of NaOH. Added milliliters of NaOH, and this is pH. So when we add 10 milliliters, when we add 0, alright, the original pH is 2.07. So when we have 0, the pH is going to be 2.07, which is over here. Now when we add 10 milliliters, it's going to be 2.54. So it's going to be 2.54. So barely increased. Or 2.5, it's past this line. So it's going to be over here. Now, when we add 25 milliliters, it's going to be 3.14. 25, 3.14. 20, so 25 over here. 3.14, it's going to be over here. And when we add 40, it's going to be 3.74. 40 is going to be 3.74. So very close to 4. Oops. Over here. There we go. When it's at 80, when it's at 50, when we add 50 milligrams over here, it's going to be pH of 7.9. So 50 is 7.9. 7.9 is over here. 50. So this is where it is. And finally, when we add 80, it's 12.523. So 80, 12.523. So about this line to be over here. So this is how our titration curve is going to look like. Let's collect the dots. Going to be here. Going to be here. And we can assume what's going on over here. And it's going to look something like this. And this will be our titration curve for this solution. And that is it for the whole problem set. Thank you for watching.